Hi, welcome to my channel, Math Made Easy with Laurel. I'm Laurel, and in this video we're going to take a look at solving trigonometric equations. The topic of solving trigonometric equations brings in a lot of stuff that we've talked about already. It brings in trig functions of any angles, which I'll talk about in a minute. It brings in the unit circle, and it brings in our trig identities. And it also brings in working with our trig functions when our angles are measured in radians. So I highly recommend that you go back and take a look at the videos on those particular topics first if you haven't yet. Otherwise you may get really lost in this video. If you remember, all students take calculus. It can help you remember the quadrants that the different trig functions are positive or negative in. So for example, in quadrant 1, all of our trig functions are positive. So sine, cosine, and tangent, and their reciprocals. In quadrant 2, the only trig function that's positive is sine, which means the other ones are negative. Cos and tan are negative. In quadrant 3, the only trig function that's positive is tan. Therefore, sine and cos are negative in quadrant 3. And in quadrant 4, the only trig function that's positive is cos. Sine and tangent are negative. Then I looked at special angles, and then from that we went to the unit circle. And I don't know if you can see it or not. The unit circle tells you coordinates of your cosine and your sine function at some special angles. The special angles are pi over 6, pi over 4, and pi over 3, and then similar angles in the other quadrants. So if you have access to that, it will allow you to find the angles in radians in exact form, which is often required in these types of equations. So we're going to refer to the unit circle. And the last thing that we'll be using is our trig identities. So I've just written them as basic identities, the Pythagorean identities, and the double angle identities. In the last couple of videos, I talked about these identities, so you can get all of those identities from those videos. Now that we're equipped with all of that, we're ready to start solving trigonometric equations. You'll know that you're solving an equation if you get these instructions such as this. Solve for values of x for x greater than or equal to 0 but less than 2 pi. So that tells us a couple of things. That tells us that we're looking at angles in a complete rotation, 2 pi radians, and it also tells us that we want to work in radians. So don't be working with your angles in degrees. If you need to find your angles in degrees and then convert them to radians, that's fine, but you're going to be expected to express your angles in radians, which are real numbers. So our first example, sine of x minus 1/2 equals 0. So we're just, first of all, we isolate the trig term. So we're going to have sine of x equals 1/2. And then we solve this just like we were solving the inverse trig functions in an earlier video. We're going to go x will equal the inverse sine of 1/2. Whenever you get a value for sine or cosine that is on your unit circle, you're not going to need to use your calculator. Remember, the coordinate for sine function is the second coordinate. So we know that sine is positive in quadrant 1 and in 2, so we're just going to look at those two quadrants. Where is the sine value 1/2? The first one is pi over 6. And then the second one will be 5 pi over 6. So having access to that unit circle saves you some time, and it also allows you to express your angles in exact values. If you used your calculator, they're not going to give you the angle as pi over 6, they're going to give you a decimal value. And I'm guessing that you're going to be expected to put the exact values with their special angles. If you don't have a unit circle and you want to use your calculator, What you could do is have your calculator in degree mode, find your angle in degrees, and then convert that to radians, and that will give you an exact value. Okay, my next example has 4 times cos squared of x minus 1 equals 0. So again, we can isolate our cos squared term. So 4 times cos squared of x equals 1. Now I'm going to divide by 4. Then I'm going to take the square root. But remember, when you take the square root, it's going to be the positive and negative value. And that can be expressed as positive or negative 1/2. So we actually have 2 solutions to this equation, and each solution typically will give you 2 angles. So let's take a look. The first one, where cos of x is equal to 1/2, so positive 1/2. So x will equal the inverse cos of 1/2. Is 1/2 a ratio that you're going to see on your unit circle? Yes, it is. So my 2 angles here will be pi over 3 and 5 pi over 3. The other solution will be when cos of x is equal to negative 1/2. So x is equal to the inverse cos of negative 1/2. Again, that's a value you're going to see on your unit circle. So we know cos is negative in quadrants 2 and 3, so we just focus there. And cos function is the first coordinate of all these points. So we'll see a negative 1/2 at 2 pi over 3. And at 4 pi over 3. So there's our 4 solutions, and you can easily check by taking each of these values and plugging into the original equation and making sure that it makes it true. Let's try some more. In our next example, we have a tangent function in more than one term. We also have some grouping symbols there. We've got parentheses, so let's get rid of those first. And then we're going to combine like terms. I distribute the 3. 3 times 1 is 3, plus 3 times tan x. I've got 4 tan x on this side. I have 3 tan x on that side. I'm going to subtract 3 tan x from both sides to get 1 tan x. I'm going to subtract 2 from both sides. When I subtract 2 from 3, I get 1. So I know my solution will be the inverse tan of 1. You may not recognize that 1 is the tangent of a special angle because we don't have the coordinate for tangent on our unit circle. However, we do know that the tangent is equal to the sine over the cosine. We could take the second coordinate and divide by the first coordinate for all of those special angles, and that would give us the tangent value. You may notice in quadrant 1 at pi over 4 radians, both cosine and sine of that angle are equivalent. So if we were to take the ratio, it would be equal to 1. So therefore, we know that pi over 4 will work. If you take the tangent of pi over 4, it's equal to 1. If that's difficult for you, you could work with your calculator and have it in degrees, and then find the inverse tan. You'll get 45 degrees, and then convert it to pi over 4. We know that between 0 and 2 pi, there are 2 quadrants where tan is positive. The other quadrant is quadrant 3. So in quadrant 3 at 5 pi over 4, cos of 5 pi over 4 is equivalent to sine of pi over 4. So if we took that ratio, we get a 1 as well. So 5 pi over 4 is our other angle. So it's a little tougher when you're working with tangent, when it's these special angles. If it's not a special angle, you just go inverse tan of whatever the value is, and then just give the radian value. But it's just when it's these special angles, you're going to be expected to write them as exact values. In this next equation, I have more than one trig function. And I only want to work with one trig function. I don't want to work with more than one when I'm solving these equations. So can I get rid of cos squared x and write it in terms of sine of x? If we take a look at our Pythagorean identities, we know that cos squared x plus sine squared x equals 1. Therefore, cos squared x will equal 1 minus sine squared x. So I'm going to substitute that in for cos squared x, and then I'll have my whole equation just in terms of one trig function. So 1 minus sine squared x now I'm going to expand and add any like terms, and then I'll see what I'm left with. So this will be 2 minus 2 times sine squared of x minus sine of x minus 1 equals 0. I like keeping it equal to 0 when I have a bunch of terms because I'm probably going to have to factor. So I have negative 2 sine squared x minus sine x. I have 2 minus 1, so it gives me plus 1 equals 0. This is an equation that I can factor, but it's tough to factor when your highest degree term is negative. So what I'm going to do, this is an equation, so I can multiply both sides of the equation by negative 1. So I'll multiply this side by negative 1, and I'll multiply this side by negative 1. So 2 times sine squared of x, negative negative gives me positive, plus sine of x minus 1 equals 0. This will be much easier to factor than the previous expression. Going back to a previous video on factoring, if I had 2m squared plus m minus 1, that's a trinomial. So that would be my factors in that expression. It's the exact same thing when I have this expression. It's just that instead of an m, it's sine of x. So my factors will be 2 sine of x minus 1 and sine of x plus 1. We learned before that when you have a product of factors equal to 0, and it only works when it's equal to 0, we can use what's called the factor theorem that says the only way that you can get a solution is if at least one of those factors is equal to 0. So either this equals 0 or this equals 0. Only solutions. And that only is going to be true when your product is 0. So therefore I'm going to have a solution if 2 times sine of x minus 1 is equal to 0. So 2 times sine of x is equal to 1. So sine of x is equal to 1/2. So x will equal the inverse sine of 1/2. We've already taken a look at that. That's going to be pi over 6. And quadrant 2 would be 5 pi over 6. The other solution is when sine of x plus 1 is equal to 0. So sine of x is equal to negative 1. So x will be the inverse sine of negative 1. There's only one angle that has a sine of equal to negative 1, and that's 3 pi over 2 on the axes. So you could write it in order: x is equal to pi over 6, 5 pi over 6, and 3 pi over 2. Again, we can check these easily enough. Plug each of those values into your equation, making sure your calculator is in radian mode, and check to see if this does indeed equal 0 when you put this value in, then when you put this value in, and lastly, when you put that value in. I want to do more examples of solving trig equations, but I would recommend that you do some of the easier ones first, and then we'll move on in the next video to some more difficult ones.